This video is going to cover a topic under digital signals processing, considered sound manipulation. We're going to be looking at two different subtopics, real-time noise cancellation and controlled sound distortion. Now, in basic overview of real-time noise cancellation, the applications we're going to be looking at are going to be completely frequency-based. So looking at the frequency spectrum of the noise and sound coming in, trying to pick out the noise itself and cancel it in real time. Now, we're going to have to make some assumptions because the noise is going to be in real time trying to get rid of it, and you can't predict that accurately. You can't know what's going to happen before it happens. So some predictions will have to be made based off assumptions. Now, there's a multitude of ways to get rid of noise. We're going to look at three different approaches in this presentation. We're going to be looking at noise cancellation due to frequency analysis. So the basic way of doing that is the Fourier transform, which converts from time to frequency data. There are some limitations based off this. It considers that you give it an infinite amount of data, which isn't realistic. And because of that, what frequency information it gives you back are all stationary frequencies. They are frequencies that it considers have happened throughout the entire signal you give it. Now, a way to fix this is by windowing. Clearly, without windowing, it still looks like you window with a square wave. The best way to do this is window with a decayed window to minimize the effect in frequency information. Now, short-time Fourier transform is applying this windowing approach and sliding the window over time, and that will give you a 2D spectrogram which will show you data in both time and frequency. So hopefully this will help you out with temporal frequency knowledge, knowing when frequencies change. Now, there's a limitation on how well it can do that. The resolution in frequency is based off how big of a window you take in time. The longer the window you take in time, the closer it approaches to the basic Fourier transform. So technically there's better resolution in frequency, but you can't really get much temporal information out of that. Again, the same problem we had with the basic Fourier transform. Now, the overall limit between how good resolution you can get in time and frequency is called the Gabriel limit. This is put in place just through the natural form of the transform. That has nothing, you can't control that without changing the transform itself. Now we're going to look at a GUI made through MATLAB to demonstrate these effects. Now, this is a short-time Fourier transform GUI made through MATLAB. We have a spectrogram over here on the right, windowing controls here on the left. We can control the type of window. Right here we have Hamming. We can look at Bartlett, which is a more triangular form, and we have the option of the rectangular window, which is essentially the more, you could say, ignorant form of just grabbing a chunk of data without really manipulating it at all. We have a couple different input signals we can give it. Discrete jumps is what you see on the right. A linear chirp is essentially a frequency that is changing linearly. We have a quadratic chirp, same approach except it's changing quadratically. And two dynamic signals, which are essentially two different frequencies changing at different rates through time. Now, for the best demonstration, we'll look at the discrete jumps to see the change in resolution. Now, you can see right here we have a fairly small size window. We'll go back to the Hamming window for less change due to leakage. And you can see right here, the smaller we make the window, let's put it down to, say, 30. Now, the resolution in frequency is terrible. You can't really even depict which frequency it's at. It looks like it's ranging from 0.1 to 0.3 on this normalized scale. But you can much better see when it changes. Now, let's change it to something much bigger. Right here, you can clearly much better see where the frequency exists. Now the range is much, much smaller. But this range in what time it changed gets blurred. So the resolution in time diminishes. How this is applied in noise cancellation. Now, let's look at, we are making the assumption that the noise does not change too drastically between samples. Now, the first approach is if you know the statistical distribution of the noise itself. We're going to use a Wiener filter, which minimizes the noise based off the distribution, and the coefficients of the filter itself get iteratively changed every sample to try to make it as accurately as possible. The second approach is assuming you have a mic outside of the system to be able to record the noise itself. Again, you're not going to know what noise is going to happen next, but you can use the noise that just happened and negate the next signal with this noise to get rid of it. Again, assuming the noise has not changed drastically. Now, in the previous approach, we literally just held the noise values from the previous sample and negated the next sample by it. In this approach, assuming the frequency of the noise is happening in a more deterministic fashion, you can apply regression and predict what the noise will be in the next sample and use that as a smarter way to negate what it would be.
Alright, I'm going to be talking about sound distortion, specifically the flange effect. Originally, this was done by essentially taking the audio that was playing in two tape machines and slowing one of them by putting a finger on the flange or the rim of the device. And this would cause a drain pipe or a sweeping effect as the two signals would go in and out of phase with each other. So this is what that would look like as somebody would record the output into a third device into its two stereo channels. So our system does something similar to this by taking one signal and then taking another of the same origin and delaying it as a function of time. So what this would end up looking like is something like this. So we have a function controlling where the other function is relative to where the second signal is relative to the first, and it continuously varies as they play. So the resulting signal that you get at your output ends up having sort of a sweeping or a pipe sound to it. So our system, unlike the diagram, actually has no feedback implemented. And we use past and future values, so it's non-causal. However, if this were a real device, such as like an electric guitar effects pedal, it would most likely be causal because you would want to have no delay in the output audio. But this made sense for us since we were operating on recordings or audio files that we already had. So now it's time for a demo. So shown here is the tool that we built to basically mimic the effects of the flanger pedal shown on the right with all of the same parameters. So here's an example of something that we distorted with the flange effect. And here's the distorted signal. Here's an example of how that can be applied with voice changing. So here's the original recording. This is a demonstration of the flange effect. This is a demonstration of the flange effect. And if we increase our delay frequency drastically, we can get a sound like this. This is a demonstration of the flange effect. The Force is with you, young Skywalker. The Force is with you, young Skywalker.